we are in position to talk about the semantic segmentation. In semantic segmentation, each pixel is classified according to the class of the object it belongs to, okay? Such as road, car, pedestrian, building, as shown in the next slide, okay? Something like this, okay? You can obviously see that each color represents that pixel belongs to a different class. For example, people class, I mean the pixels are represented by in red, okay? And for the building, okay, the pixel is represented in brown, okay? Road, the pixel is represented in gray, and so and things like that, okay? So so the main difficulty in this task is that when images go through a regular CNN, they generally lost their spatial resolution, okay, because subsampling, okay. So regular CNN may end up knowing that there's a person somewhere in the bottom left of the image, but it will not be much more precise than that, okay. So there's such an issue for the regular CNN. Okay, so just like for object detection, there are many different approaches to tackle semantic segmentation. Okay, some are quite complex. Okay, however, a fairly simple solution was proposed in 2015 paper. Okay, by Jonathan Long. Okay. I mean, we talked about this guy, okay, the same guy, I mean, earlier, okay, but at a different place, but I'm getting old, I forgot where we talked about this Johnson. Okay. So we discussed, so this author, okay, the authors start by taking a pre-trained CNN and turning that pre-trained CNN into a FCN. So, oh yeah, I remember. It's this guy who proposed the FCN. Okay, so this FCN is his contribution. Okay, the CNN applies an overall stride of 32 to the input image. Okay, so the image becomes like very small. Okay, the last layer output feature maps that are 32 times smaller than the input image. Okay, so this is clearly too coarse. Okay, not precise enough. So they add a single upsampling layer that multiplies the resolution by 32 because eventually we need to identify what class each pixel belongs to. So you need to and the pixel, the class each pixel belongs to, I was talking about the pixel in the original resolution, right? So if the image becomes such this small, okay, obviously the one pixel is no longer represent a single pixel in the original image, right? So you need to upsample the image, okay, meaning enlarge the image back to its original resolution, okay. So for upsampling, okay, there are several solutions available for upsampling, okay. For example, you can do bilinear interpolation. Okay, they only works reasonably well. Okay, to 4 times or 8 times. Okay, what we call bilinear interpolation is like originally, if you want to double the height, okay, the height and width, you just originally for the consecutive pixel, you insert 1 pixel in between. Okay, then the height and width will be doubled, right? Okay, and the pixel that you insert, okay, will be, interpolated. Okay, the intensity of that pixel. Okay, will be interpolated from the neighboring pixel intensity. Okay, so that's like doubling the image width and height. And you can do the similar thing for to enlarge image to 4 times or even 8 times, and you get a reasonably okay image. Okay, but if you want to upsample the image to bigger than 8 times, okay, you can use what we call transpose convolution layer. Okay, it's equivalent to first stretching the image by inserting empty rows and colors. Okay, these empty rows and colors contain all 0. Okay, then performing a regular convolution. Okay, so some people prefer to think of it as a regular convolution layer that use fractional stride. For example, 1 over 2. Okay, then it's like you double the width and height. Okay, so it's something like this. Okay, so you can see we insert the extra row and column. Okay, in between the original pixel. So the original pixel are 2 by 3, and we insert extra rows and columns in between these pixels. Okay, and then we use a regular convolution. Okay, to create the next layer. So this is called transpose convolution layer. Okay, and in this case, it's considered, well, even though we say this stride is 2, but actually we consider this as like a fractional stride, like 1 over 2 stride. Okay, so the transpose convolution layer can be initialized to perform something close to linear interpolation. But since it is a trainable layer, okay, it will learn to do better during training. Okay, so it can learn better during training. Okay, in TF.keras, okay, you can use the comp2D transpose layer. So TF.keras, okay, it's a keras under the TensorFlow. comp2D transpose is provided. Okay, so you can create this transpose convolution layer easily. Okay. So in the transpose convolution layer, okay, the stride defines how much the input will be stretched, not the size of the filter steps. Okay, so when we specify 2, stride equal to 2, that means we stretch the width and height. We double the width and height instead of shrink the width and height by half. Okay, of course it's in the comp2D transpose function. Okay, so it's different from the regular convolution layer or pruning layer. So this solution is okay, but still too imprecise. Okay, so to do better, okay, we need to add skip connections from the lower layers. Okay, so it's actually something like this. They upsample the output image by a fraction of 2. Okay, and they add the output of the lower layer that had this double resolution. Then maybe I'll just show you this. So this is the visual map. First, it's downsampling. And then they use upsampling. Okay, so first we double the width and height. Okay, and then when they double, I probably should use double. When they increase the width and height to like 60 times, because eventually they need to, 32 times. Remember? Okay. Okay. They need to increase the width and height by 32 times. Okay. So what? The Johnson norm case is something like this. Okay. Before that, there are like a kind of like you get like the pre-trained model, and then you do like certain transfer learning, a little bit of training on that, and then this is the intermediate feature map, and you use downsample to reduce the size, and then you need to increase this to 32 times, right? Both width and height. So first you double this, the width and height, and then you increase width and height by 16 times. But you not just do that alone, okay? You actually use skip connection, okay? From the lower layer, in order to get more information from the previous feature maps, okay? And by doing this, okay, they have enough information to make the output, feature map, like the large feature map, like more realistic. Okay, so this is like what they do. Okay, for the semantic segmentation, you can see skip connection, like another use of skip connection. Skip connection actually is very useful in many applications. Okay, so once again, there are many GitHub repositories, okay, that provide like TensorFlow application of semantic segmentation, including, but at the time when this textbook was written, okay, there were only TensorFlow 1 implementation of semantic segmentation model now. But now I'm sure there are many TensorFlow 2 implementation of semantic segmentation. Okay, this is the last slide. Okay, I accidentally hit the. Okay, so I'm sure there are TensorFlow 2 implementation available in the GitHub now. Okay, so and you will even find pre-trained instant segmentation model in the TensorFlow model project. Okay. Instead, instant segmentation is similar to semantic segmentation, but instead of merging all objects of same class into one big block, each object is distinguished from each other. Okay, so it's like okay. For example, you see many several different bicycles here, right? So each bicycle, the pixel for different bicycles will be separate instead of like represented all in the same color. Okay, and also you can see multiple cars on the street, right? But all the cars, their pixel in this case are represented in blue, right? In blue color. But in the instance segmentation, okay, each car, the pixel for each car will be separate. Okay, so this is like something. It's different from the semantic segmentation. Okay. So. Okay, so at present, the instant segmentation models available in the TensorFlow models project are based on mask RCN architecture. Okay, there's a mask RCN. This is another model that's originated from RCN model. Okay, so which was proposed in 2017 paper. Extends the faster RCN model by additionally producing a pixel mask for each bounding block. So not only do you get a bounding box around each object with a set of estimated class probabilities, but you also get a pixel mask that locates pixels in the bounding box that belongs to that object. So this is like the semantic segmentation. But we don't have a picture in this slide for you, but you get an idea. And in TensorFlow, okay, they also offer a few other kinds of convolution layers. Okay, for example, keras.layers.conv1d, this instruction can create a convolution layer for 1D input, okay, such as time series or text input. Okay. Text input, of course, it's you can use CN or NLP, okay, natural language processing. But we will not talk about natural language processing in this class because our department has another professor to offer natural language processing class. I think that professor will cover this subject much better than I can possibly do. So I will leave that part to him. Okay. So keras.layers.conv 3D, it can deal with 3D input. Okay, such as 3D Pascal. Okay, Pascal is positron electronic scanning, okay, which is used in the hospital, okay, to reconstruct like a 3D image of your body, okay. So the data set is 3-dimensional. So if you want to do convolution over 3-dimensional input, so this is the thing, okay. And there's a dilation rate, okay. Say dilation rate type parameter of any convolution layer, okay, to a value of 2 or more creates a Charles convolution layer. Okay, this is in French, okay, or withholds. Okay, so it's like you intentionally create holes in between the input. Okay, so this is equivalent to using a regular convolution layer with a filter dilated by inserting rows and columns of 0. So it's kind of similar to concept is kind of similar to transpose convolution layer, but it's slightly different. Okay, and so for example, okay, 1 times 3 filter equal to this one may be dilated with a dilation rate of 4. Okay, so if that's the case, okay, then you can see this input 1, 2, 3 will be, there will be 0 inserted in between 1 and 2, and in between 2 and 3. So 1 and 2, the distance will be 4, and 2 and 3, the distance becomes 4 as well. That's because the dilation rate is set to be 4 here. So this lets the convolution layer to have a larger reception field and no computational price, and use no extra parameters. So this is like, it works similar to transpose convolution layer, but it is for different purpose. Okay, because it's it try to make you, ensure you have a larger receptive field. Okay, and TF dot depth width come to the, okay, can be used to create depth-wise convolution layer. I think we talk about depth-wise convolution layer, right? But you need to create the variables yourself. So it applies every filter to every individual input channel independently. Okay. So if there are Fn filters and Fn prime input channels, then there will be output. It will output Fn times Fn prime issue maps. Okay. So this depth-wise convolution layer, I think we talked about that earlier. So that's about it for this chapter. Any question? Well, I was hoping that we can finish this chapter much earlier, okay? But obviously, well, we couldn't do that. But at least we get it done now, okay, today. And so now it's about time that we move on to the next chapter. Okay. I will make sure this slide to be uploaded to eClass today. Okay, I'm sorry about that. Okay. So, so this chapter talks about sequences using RNN and CNN. Okay. To be honest, most of this chapter talk about RNN. Okay, but still, like there are some examples that are about for CNN to handle sequence data type. Okay. So, for example, like when in a baseball, okay, when the ball was hit, okay, the outfielder, you'll see outfielder immediately starts running, right? The outfielder will anticipate the ball's trajectory. Okay, so so at the time when the batter hit the ball, the outfielder immediately can guess, okay, the ball's trajectory, okay, rough location where he can get the ball. Okay, so he tracked, okay, adapts his movement and finally catch it. Okay, so of course, like audience will give big props. But the issue is, okay, this whole tracking, whole catching thing, okay, performed by the outfielder is the ability for human, okay, to anticipate, to predict the future. You know, it's a you know, actually we have such a similar ability as well. Okay, it's not like only the outfielder can have such ability to predict what is going to happen or to anticipate, okay, or the ball trajectory. But of course, like outfielder is better at that, and outfielder can run faster to catch that ball. But let me give you some example. For example, like if you have a very good friend, okay, when you chat with your good friend, okay, your friend trying to tell you something, and you are able to, before he or she finish the sentence, you are able to finish your friend's sentence, right? You anticipate what your friend is going to say, right? So this happens. I'm not going to say all the time, but sometimes, right? Of course, this probably only happens between close friends, okay? And also, like, you can anticipate the smell of coffee at breakfast. In Taiwan, we probably don't have that, but for example, okay, a better example in Taiwan, okay, for among Chinese, okay, it's like water in your mouth, right? You start having running water in your mouth. It's not like you already taste the plum, but you start to have. I mean, you can your brain anticipate that the plum is sour, so you start producing the running water in your mouth. Okay, we have such a slang called 望梅止渴, right? Okay, so everybody, almost everyone, has such ability. Okay, it's not just all you. Okay, so we are able to predict the future. Of course, in a certain, just to a certain point, not exactly like a long future, but we can anticipate something is going to happen. Okay, they can analyze time series. We are able to analyze time series data. Okay, and as a stock prices, and they tell you when to buy or sell. Okay, sorry. So recurrent neural network also has that ability. So you can use recurrent neural network to analyze time series data, such as stock price, and tell you when to buy or sell. Or in autonomous driving system, the recurrent neural network can anticipate car trajectories and help avoid car accidents. Okay, this is actually like one of the primary research topic in my lab. Okay, so more generally, okay, they can work on sequences of arbitrary length rather than on fixed size input, like all the network that we have considered so far. Okay, so for example, they can take sentences, documents, or audio samples as input, making them extremely useful for natural language processing applications, such as automatic translation or speech to text. But for that part, okay, using the RNN for NLP, again, we are not going to talk about those aspects because, as I said, okay, our department has another class dedicated for natural language processing, so I will leave that part into that professor. Okay, so this chapter we are going to introduce recurrent neural network, but just to a certain degree, and there are great applications of recurrent neural network, especially in natural language processing. But for that chapter, I'm going to skip that. Okay, for those of you interested in that, okay, you can either read that chapter yourself or go to take that natural language processing class. Okay, so in this chapter, we will first look at the fundamental concepts underlying RNN and how to train them using backpropagation through time. Okay, so this is a new term called backpropagation through time. Okay, then we will use these RNNs to forecast the time series. After that, we will explore the two primary difficulties that RNN faces. Okay, first is unstable gradient. Okay, we discussed unstable gradient, vanishing gradient, exploding gradient in chapter 11. But okay, for RNN, it's going to be even more difficult. Okay, because the backpropagation through time, okay, increase like the chance for unstable gradients to happen. Okay, so which can be alleviated using various techniques, including recurrent drop-off and recurrent layer normalization. Okay, we are going to talk about later. Okay, and a very limited short-term memory. Okay, for RNN neural. Okay, but that thing can be fixed by using LSTM and GRU cells. So what are LSTM or GRU cells? Okay, we are going to talk about them later. Okay, so RNN are not the only types of neural network capable of handling sequential data. For small sequences, a regular dense network can do the trick. Okay, so MLP is fine for small sequence data. Okay, and for a very long sequence, such as audio samples or text, convolutional neural network can also work quite well too. Okay, so at the end of the chapter, we are also going to discuss, okay, these possibilities. We'll finish this chapter by implementing a wave net. This wave net, you can first this is a CNN architecture, and judging from the name, obviously you can tell that this wave net is used to handle the audio sample, okay, audio input, sequences of tens of thousands of time step, because audio sequence, you know, like the audio sample, like the sampling rate is very high. Okay, so in chapter 16, we will continue to explore RNN and see how to use them for natural language processing. Chapter 16 is dedicated to MLP actually, okay, along with more recent architectures based on attention mechanism. Okay, but this part, chapter 16, we are going to skip that, unfortunately, because I don't want to, step on somebody else's territory. Okay, if you are interested in this, again, as I said, like, you are welcome to take MLP class. Okay, so well, we only have like about 10 minutes left. Okay, so I guess we can still talk about recurrent neurons and later. Okay, so so what is recurrent neuron? Okay, what's the difference between recurrent neuron and the regular neuron? The regular neuron that we already know regular neuron. Okay, it takes a couple of multiple inputs and try to do the computation. Okay, try to compute every the weighted sum of the input, and then apply the activation function, right? And then output, right? So the direction for the regular neuron is one dimensional, from the lower layer to the upper layer, right? So it's people this type of neuron, okay, construct is a building blocks for the people neural network, okay. Except it also has connections pointing backward, okay. So the recurrent neuron, okay, is similar to regular neuron, but we have connection that pointing backward. So let me show you. So this is the recurrent neuron. So if we try not to look at this, then this is basically regular neuron. Okay, of course you can also take multiple inputs here, but the issue is, okay, among its input, actually one of the input actually is from its previous output. This is something that is very special about recurrent neuron. Okay, so we have so this is the recurrent neuron architecture. Okay, so if the input is X and output is Y, in the next step, this Y will be the part of the input for this neuron again. Okay, so if you try to unroll through time, okay, we try to observe the behavior of this neuron, for a period of time. What happens is that, okay, all this represent the same neuron. Okay, so this is like the time step, the input for the time step t-3. Okay, and then okay, this will produce y with time step t-3, and the y t-3 will be the input for the same neuron. Okay, along with the next input x t minus 2. And with these two inputs, this neuron will create y t minus 2. And again, this will be fed back to the same neuron again and again. So this is the important difference, okay, between the recurrent neuron and the regular neuron. Because the recurrent neuron has this feedback mechanism. Okay, so at each time step t, okay, for time step we can also call it frame. Okay, basically that represents the same meaning. Okay, so this recurrent neuron receives the input xt as well as its own output from the previous time step yt minus 1. Okay, since there is no previous output at the first time step, it is generally said to be 0. Okay, at the beginning, at the very, very beginning, because we don't have this neuron doesn't have, we don't have the previous input output from this neuron. So at the very, very beginning, okay, that extra input from the feedback is said to be 0. So we can represent this tiny network against the time axis as shown in the figure on the right. So we call that unrolling the networks through time. Okay. So this is about one neuron, right? This is about one neuron. So you can easily create a layer of recurrent neurons. Okay. At each time step t, every neuron receives both the input vector xt and the output vector from the previous time step yt minus 1. Okay. Originally, we consider this yt minus 1, okay, as a number because this is just one neuron, so the output only output one number. But now, okay, when you have a layer of recurrent neuron, a number of recurrent neuron, okay, all these outputs will be fed back to every neuron in this layer. So each recurrent neuron has two sets of weights, one for the input xt and the other for the output of the previous time step yt minus 1. So we call this weight vector wx and wy. So if we try to write it in a matrix format, it's going to be something like that. How do we call this Greek letter? Phi, right? So phi, okay. This phi is the activation function. So inside this, it's basically like weighted sum of the input wx, okay. So input xt, okay, multiplied with the weight, okay, plus the previous output yt minus 1, okay. Xt and yt minus 1 are both vector, okay, and multiplied by the wy, okay. This is transpose, okay. So that this is like you can consider this as the inner product of two vectors, okay. So both of them will produce a number, okay, and then you add up the bias, and the whole thing will become number. And this number will go through this activation function, and you have the new output. Okay, so this activation function could be real, it could be something else. Okay, so it's up to depends on what the activation function that you will be using. Okay. So if you draw the picture, it's going to look like this. Okay, so each of these will output a number, right? So the collection of this number will become a vector y. Okay, and this will be the output, and also this will be the feedback. Okay, to each of the neurons, each of these recurrent neurons. Okay, and you can also consider back propagate unroll through time for the whole layer. but it's going to be something like this. So y0 is going to be y1, y2 are all vectors in vector shape, vector format. Okay, x0, x1, x2 are all vectors. Okay. So, okay, so we already talked about this output. It can be written like this, right? So we can actually rewrite this formula to be something like this. Okay, x t y t minus 1. We put them together, okay, and then multiply by w, and w is of the shape like wx, wy, okay, in this. So you can imagine, okay, this thing times this w is going to be come back to this shape, right? Okay, so this is just like a different way, a more concise way to write this formula. Okay, there's really nothing different from the previous one. Okay, so each of them, I think like you can check out like the description of this yourself. Okay? We're not going into the detail here. Okay, very good. The description here, basically, try to tell you the dimension of each matrix, okay, and to tell you that okay, they match without any problem. Okay, because multiplication between matrices need to, need to follow certain rule, right? So this one make sure like that those rules are met, but I think those are key. Okay. So 2 points to note. Okay, yt is a function of xt and yt minus 1. Okay, and this yt minus 1 again is a function of xt minus 1 and yt minus 2, and so on. So you can sort of consider yt to be a function of xt minus 1, xt minus 2, xt minus 3, and so on. Okay, so up to x0. Okay, so many researchers, so you can consider sort of like the yt is produced by all the previous input. Okay, not just the current input, but also by all the previous inputs. Okay, so in some sense you can consider the recurrent neural network has memory. Okay, because it considers all the inputs, not just the current input, to produce the current output. Okay, so and also another point. Okay, many researchers prefer to use hyperbolic tangent, activation function in Rn rather than the real activation function. Okay. However, ReLU-based arguments are also possible. Okay. I don't want you to consider only use hypertangent activation function for Rn. Okay. This is not always the case. ReLU-based arguments are also commonly seen nowadays. Okay, so this is another point I want you guys to be aware of. Okay, so because the current output is produced, the current output can be considered as the result of all the input, not just the current input. So you can consider the neural network has a certain memory. Okay, so we call this recurrent neuron as a memory cell. Okay, memory cell. A single recurrent neuron or a layer of recurrent neuron is a very basic cell. Later in this chapter, we will look at some more complex and powerful type of cell. Okay, so in general, cell state, the time step t, denoted as h of t. Okay, the height, h stands for the hidden, because it's a hidden state. Okay, it's a function of some input at the time step and its state at the previous time step. So ht equal to f, ht minus 1, and xt. So actually, a lot of time, the ht will be the same as yt. Okay, its output at time step t, you know that's yt. It's also a function of its previous state and the current input. So in the case of the basic cell, we have discussed now, okay, the output is simply equal to the hidden state. But more complex cell, for more complex cells, this is not always the case. Okay, we will show as shown in the figure in the next slide. Okay, so this slide you can see. Okay, we have output y, but the hidden state is actually what is fed feedback to the cell. Okay, so now in the previous example, we can see the output and feedback are the same. But now we try to distinguish the output and feedback. Okay, this is more general, but for the basic cell, these two are the same. Okay, but for the future, more complicated cell structure, okay, they may be different. Okay, so well, I think we are out of time today, so we'll stop here. Next time, we will start from here, input and output sequences. Okay. Any question? Okay, if no question, we'll stop here, and I'll see you guys again next week. Okay. So again, let me remind you, the project 3 has already been uploaded to the class. Please check it out. Project 4, please remember to find another group to form a big group, okay, before next class, if you haven't done so. And, I will upload the final project today, okay, as well as this set of slides, okay. Any question? Okay, so no question, I'll call it a day.